Hi everyone, my name is Katie Kayan.
I'm Kelly Sue,
I'm Hikaru Kotake.
and we will be explaining this illustration, which relates to the biotoxicity experiment we did earlier this week. As you can see, there are several robbers, all varying in different sizes, right? Like right here. And these sizes are dependent on their weight. So this guy is like the lightest, so he's the smallest, medium, and largest, right? So the first robber is capable of going through the window and is able to steal the TV, so window and TV, and from the house. The middle-sized robber is able to go through the front door and is able to steal a lot more stuff than the first robber. The last robber decides to go through the chimney, which he doesn't fit through and can't steal anything. So the second portion of the photo shows a police officer arriving to the scene of the house and dictating what has happened to the house. Since the first robber did not steal much from the house, the police officer believes that he can handle the issue on his own. Whereas since the second robber stole a lot from the house, the police officer decides that he needs backup. And since the third robber didn't steal anything, he just leaves it as is.
So for our experiment, we basically used different forms of silver in order to kill yeast cells, and this was our way of measuring the toxicity of the silver. So the three different forms that we used were silver ions, silver nanoparticles, and silver powder. So in this drawing, you can see that the first robber, which it weighs 120 pounds and is the lightest, represents the ions, which are the smallest. The second robber represents the nanoparticles, and the third robber, which is the biggest in weight, represents the silver powder. And so all three forms of this silver, they damage the yeast cells in the same way by destroying the membrane of these cells, and they do so by making the hydrophobic part of this membrane, which is the water-hating part, into a hydrophilic part or a water-loving part. And in doing so, this destroys the membrane by breaking it apart. And so all three of these forms of silver, they get into the cell in different ways. So the first robber, which is the ions, he gets in through the window. And because ions are charged, they have to go through active transport and get in through the ion channels. And in this case, the window accesses those ion channels. The second robber, or the nanoparticles, because the nanoparticles are very small and they're neutral, they're able to be taken directly into the cell through endocytosis, which you can think of as the cell basically gulping up the nanoparticles. And so in this case, the robber goes in directly through the door without any difficulty. And the third robber, which is the largest, this represents the powder. And because the powder is so big, it can't get into the cell directly. And as a result, only some of these ions can get in. And you can see that the robber can only fit in some of its parts through the chimney. And also, in our experiment, we measured the health of these cells by seeing how much carbon dioxide they produce through cellular respiration. And this was our form of seeing whether they were alive or not. And this is shown in the illustration in the bottom half of the picture, where the illustrator tried to show how the police would respond to the damage done by the cells. And as you can see, the nanoparticle, which does the most damage, the police responds in the most serious way by calling for backup.
So one of the limitations of the key points missed in this illustration was the ratio of the robber's weight. In actuality, the ratio of the different forms of silver are massively different, while the drawing has the robber's weight relatively closer to each other. Another limitation was for the silver powder, or the biggest one. The drawing here shows the inability to enter the house, but really some ions do go through the house. Also, one of the concepts that they didn't get through was the concept of different charges. Silver ion, which is this one, they have the difficulty of entering because of the positive charge, and a nanoparticle has the easiest time to enter. If the door had like a no happy people sign, and that didn't allow the Ag plus or the positive 1 ion that is respective to their positive behavior, it would force the ions to go not through the door, but the window here, which acts as the ion channels in this case. That is all. Thank you for listening.
Thanks.
All right, so now's the time where we ask for questions from the audience. We would love a parent or colleague or instructor to start this off. And for the presenters, please repeat the question that they ask so that, again, our live streamers can hear, and just to make sure that everyone here hears as well. So questions?
Yes? Oh, okay.
Yeah.
My question had to do with how you measured the response of the, I guess in your analogy, the least response in your experiment. How do you measure the severity of the response?
So
We had a device called a manometer where it's like a tube, and there was a stopper at the end of the tube with like a what?
Liquid.
Oh, well, yeah.
Yeah,
So
so-
there was like a stopper at the end of the tube, which we put on top of the flask. Inside of the manometer, which is like a tube that leads out, we put liquid like inside, and then we measured the distance where the liquid moved.
So it would be
So like the nanoparticles, they did, so when we put the nanoparticles in with the yeast cells, they produced the least amount of carbon dioxide, which showed that they were the least alive. And in that way, the nanoparticles were able to kill the yeast cells the fastest. And this was followed by the ions and then the silver powder. So like in this image, you can see that the police, the second robber, the police has to call for backup because the damage was so severe. And this would show like how the nanoparticles killed the cells the most. And then the first robber, since the damage was only a little, he thinks that he can go after the robber himself. And in the last one, the last robber, nothing happens, so the police doesn't need to go after them.
So in our experiment, the more carbon dioxide that was produced, the more alive.
No. The more carbon dioxide that was produced, that meant that the yeast cells weren't killed as fast.
Yeah.
So the less amount of carbon dioxide that was produced, the more the yeast cells were killed.
So the equal amount of the liquid was pushed by the carbon dioxide, and the difference it showed.
Yeah, that's what we measured.
Any other audience questions? Yes?
Yeah.
On the second example where you said the police had to call the backup, what is the backup? Who's the backup?
So his question was for the bottom part, the second part, who was the backup? And we're not sure who the illustrator was trying to call for backup, but I would assume it would be other
Police officers, yeah.
Yeah.
I have a question. So you mentioned very correctly that one of the limitations of this drawing was that it would be difficult to represent the true differences in size between the ions versus the nanoparticles versus the bulk silver. Can you guys share what those actual sizes are?
So an ion is less than a nanometer, I believe, whereas a nanoparticle is like
Oh, so the nanoparticles that we created were about 8
8
nanometers in size.
whereas like the ion is like less than a nanometer.
And then for the powder, you can see,
see
you can
it.
actually see it.
So it's
yeah.
larger, yeah.
And I guess just one more generally for the audience, how big is nano roughly?
10 to the negative 9
Yeah.
meters.
So in other words, like if it was a fractional thing with a meter, do you know what fraction of a meter it would be? Do you remember that?
Wait, no, 1 billion?
I think you just said it. You want to say it?
1 over 1 billion?
Yeah, exactly.
Okay.
So a nanometer is a billionth of a meter, exactly. Good. Any other questions? All right. Thank you, ladies.
Thank you.